Homework last night, page 153, questions 1 and 2. Any issues with either of those questions? Number 2? Anybody for number 1, or are we good with that one? All right, number 2 it is. Let's do questions 1 and 2. Okay, number 2 is more of a quantitative question. Number 2 is more of a qualitative question. Seamless, isn't it? Number 1, we get this 55-kilogram bungee jumper that's fastened onto one end of the cord made out of an elastic material. That's kind of important, you know, that the bungee cord is made out of an elastic material. Anybody ever read the Darwin Awards? There's Darwin Award books, like all kinds of them in a series. Do you guys know what the Darwin Awards are? Basically, to win a Darwin Award, most people receive one after death, after they've died. But there is the odd circumstance in which you can win it before you die. Okay, but a Darwin Award is awarded to people that have basically that are so stupid that and have taken themselves out of the gene pool because of their stupidity. Not usually on purpose. It's usually by accident. For instance, this one that I read about. These guys had been drinking, and they're on this bridge that's got some repair work. They're doing some repair work to this bridge. So it's late at night. These guys are on this bridge, and they decide they're going to go bungee jumping off this bridge. But there's no elastic cord. But there's a steel cable right there that one of the guys attached himself to, his leg to, and then he jumps off the edge of the bridge. He didn't actually win a Darwin Award because he actually survived. He ripped his leg off, like literally ripped his leg right off. But he survived. He got rescued and survived. He didn't take himself out of the gene pool, so that he didn't win a Darwin Award. Most times you actually have to kill yourself so that you're taken out of the gene pool. Although every once in a while someone gets a Darwin Award, not by killing themselves, but by just taking themselves out of the gene pool some other way. So basically by, damage to pretty important areas that prevent them from reproducing and being part of the gene pool. Anyways, this guy gets an honorary. He gets an honorable mention, they called it, because he almost took himself out of the gene pool, but not quite. Go to the bookstore and buy a Darwin Awards. They're all great. Anyways, this lady is jumping off the bridge with an elastic material, which is good because she doesn't want to rip her leg off. The cord is stretched. It exerts an elastic force directed up on her. We want to find the acceleration at the instant the cord exerts an elastic force of 825 upwards on her. So let's draw this lady jumping downwards on this bungee cord. We have two forces acting on her. There's the force of the cord. We'll call it Fc upwards. And there's a force of gravity acting on her downwards. Now, we don't know which force is bigger right now. So it doesn't really matter how long we draw those forces because we don't know which one is a bigger force. If we know that one is bigger than the other, then we should draw them proportional to that. Fg is 55. You know what? We'll worry about that, the calculation of that force later. Let's now just say the net force is equal to the sum of the forces, Fg plus Fc, the force of the cable. Now, the mass of this lady is 55 kilograms. We want to find the acceleration of her. The force of gravity is 55 times negative 9.81. It's a negative force because it's downward. Plus the force of the cable. Well, the force of the cable, or the elastic, actually changes. As it stretches more, the force becomes bigger. But at this time, at this moment, the force of the cord is 825 newtons upwards. So let's plug that in there. Okay, let's say 55 times negative 9.81 becomes a negative number. Take that away from 825. Take that over to the other side by subtracting, by subtracting or adding? Yeah, we don't have to take that over to the other side, right? 55 times negative 9.81, take that away from 825, and then we'll divide that by 55. And when we do that, we should get 5.2 meters per second squared. So she's moving downward, but yet we have an upward acceleration. How's that possible? She's slowing down. She's moving downward, but she's slowing down. That requires an upward net force, right? So therefore, we get an upward acceleration. All right? Now let's look at question 2. It says, during a bungee jump, the velocity of the 55-kilogram woman at the lowest point is 0 when the cord stretches to its maximum. You guys have seen this, right? Has anybody ever gone bungee jumping here? Yes? Where'd you go bungee jumping? Okay. Was it a big fall? Yeah. Yeah. Do you remember it clearly? Or did you kind of just block it out? Okay. There's a lot of things that I would like to do. Bungee jumping is not one of them. I have no desire to ever go bungee jumping. It terrifies me. But I've seen it before. I've seen people bungee jump before. When they bungee jump, you know that cord stretches. You can picture it in slow motion, right? That cord stretching and stretching and stretching and stretching until at some point the guy on the end of the bungee cord stops, right? So it's maximum stretch when the person on the end of it has stopped. We want to compare the direction of her acceleration at the lowest point of the jump to the direction of the acceleration when she's accelerating due to gravity. Let's look at it over here, question 2a. When she's accelerating due to gravity, so in other words, before the cord has begun to stretch, which way is her acceleration? She's free falling right now, right? Which way is her acceleration? Downward, right. It's downward. So initially, her acceleration is downward. When the cord begins to stretch and she starts slowing down, which way is her acceleration at that point? Now, she hasn't stopped yet. She's just slowing down as she moves downward. Which way is the acceleration? It's upward, right? We just established that in question A, right? Her acceleration is upward. What about when she comes to a stop at her lowest point? Which way is her acceleration then? Or is there an acceleration then when she stopped? She's only stopped briefly, right? But she stopped. Is there an acceleration? And if so, which way is it? How many people say there is not an acceleration at that point? How many people say there is an acceleration at that point? Okay, about half and half, those of you who answered there. Javi, why do you say there is an acceleration? She stopped, right? Okay, so as the cord is stretched, there's a force pushing up or pulling up. Regardless of whether it's fully stretched or not, the force is pulling up on her, right? As she's slowing down, the force is pulling up on her to slow her down. As she's stopped, the force is pulling up on her to get her moving upwards again, right? If there's a force, there's an acceleration. Which way is that acceleration when she's at the bottom point? Upwards. I think that takes care of question B as well. What's the direction of her acceleration when she reaches the bottom point? A lot of people think there is no acceleration because she stopped. No, there is no velocity because she stopped. There's an acceleration because she's only stopped momentarily and her velocity is still changing. It was negative, 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 stop, positive, 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 and she starts going back up into the air. Right, Liam? Right? Is that good? Okay, let's real quickly take a look at one more type of application that we see for these multi-force problems. This one is going to involve a pulley. Now, this doesn't seem that hard at first glance, but when we draw a free body diagram for this, all of a sudden it seems like it may be a little bit more difficult. We have a force of gravity acting down on this 25 kilogram object. We'll call that FG1. We have a force of gravity acting down on this object. It's a little bit bigger because it's a heavier mass. We'll call that FG2. So far, so good, right? The net force is equal to the sum of the forces. That's Fg1 plus Fg2. The net force is the mass times acceleration, but the mass here would be, what, 60 kilograms. Let's get the value of Fg1. 25 times neg 9.81 plus Fg2, which is 35 times neg 9.81. Both downward forces, right? So both negative, is that right? Here's where the trick comes in on these questions. They're both downward forces, but they oppose each other. One is pulling the system this way, the other one is pulling the system this way. They're opposing forces. I don't like to draw my free body diagram like this at all. What I like to do is pretend that I'm straightening it out. Pretend that I'm taking the 25 kilogram object and moving it up like that, and the 35 and moving it up like that. So that now I have a 25 and a 35 like this. If I move the 25 up like this, then the force of gravity, Fg1, that acts on the 25 will be to the left, and the force of gravity that acts on the 35 is to the right. Is there ever really a force of gravity acting to the left or to the right? No, gravity always acts down. But if I draw it like this, what does it help me remember? What does it help me to do? Yep. Right. It reminds me that one of them has got to be negative and one of them is going to be positive. Despite the fact that they are both technically down, we have to make one of them positive because they're opposing each other. Now, it doesn't really matter which one you make positive and which one you make negative. It's not critical that you draw the diagram the way that I just drew it. I just find it helps me to remember to make one of them positive. Okay, when I draw it this way, by default, I'm going to make this one positive. But again, it doesn't really matter. Okay, if you can draw it the other way and always remember that one of them is going to be positive, then do it. Doesn't matter which one you make positive. But many of you will try that and still forget to make one of them positive. So my recommendation is to draw it the way that I have there, just to avoid that possibility of making that mistake. All right, so now we've got, what is it, 60 kilograms times the acceleration. On the right-hand side, we've got 25 times negative 9.81 plus 35 times positive 9.81. That gives me 98.1, I think, isn't it? On the right-hand side? Yep. No. When I draw it this way, okay, it looks like that this one has to be positive, right? But in the end, that's only because I've drawn it this way. This diagram is no more correct than the original diagram I do. In fact, the original diagram was a little bit more correct than this one. This only helps me visualize it. So don't think necessarily because Fg2 is drawn to the right here that it has to be the positive one. It's just the one that I usually make positive because of my diagram. But it could be negative as long as you make the other one positive. So I got 60 times A is equal to 98.1. You could have gotten 60 times A is equal to negative 98.1, and that would be correct as well. So let's take the 60 over by dividing. 98.1 divided by 60 is going to give me about 1.7, 1.635. And with the way that I have it drawn, it's going to be a positive 1.6. Yours could have been negative as well, and that would have been right. So we went from problems like this, like in the quiz you had yesterday, where you had forces going in different directions on a horizontal surface, to questions like this, where you had a skydiver or a guy in an elevator, to now all of a sudden questions with pulleys in them. What's really different about those questions? What's different about them? Fundamentally, nothing. That's the point that I want to make here, right? Is that we have more than one force acting on each of them. We draw a free body diagram. We set it up, F net is equal to the sum of the forces. Plug them in and solve. They're all the same question. Okay, we're going to see that so many times this year and next year. This whole F net is equal to the sum of the forces. When we have more than one force acting, this is what we do. Even if one time it's two forces of gravity, and the next time it's a force of friction and an applied force. Doesn't matter. F net is equal to the sum of the forces. Plug in your numbers and solve. All right, let's take a look at one more example. I don't want to do these practice problems because they don't really fit. One more example, similar type thing, and then we'll set you free on a couple practice questions. This one says a 20-kilogram truck tire, object A, is lying on a horizontal frictionless surface. The tire is attached to two light ropes that pass over light frictionless pulleys. The hanging pails B and C. Pail B has a mass of 8, C has a mass of 6. What's the magnitude of the acceleration of the system? Well, this has a mass of 8 kilograms. This has a mass of 6 kilograms. There's a force of gravity acting down here. We'll call it FGB. There's a force of gravity acting down here. We'll call it FGC. What do I want to do with this? I'm sorry? Straighten it out. Yeah, pretend the pail B is going up here and the pail C is going up here. That leaves me with something that looks like this. Tire A that has a mass of 20 kilograms. The pail that has a mass of 8 kilograms. The pail that has a mass of 6 kilograms. We got a force of gravity. FGB acts to the left. And we have a force of gravity, FGC, that acts to the right. Now, technically, there are two more forces that act here, but we don't have to take them into account. What are they? Yep. Yeah. They cancel each other out, right? Okay, in these diagrams, I usually just leave them off because it kind of clutters it up a little bit, although technically they should be there. Okay, we can do this now. Same as the last question, right? Except we have three objects. FGB plus FGC. The total mass. Hey, what mass do I use here? 8, 20, or 6? Or some sort of combination of those. What mass do I use? This is like the old semi-truck with the ice cream inside, right? If we're analyzing the whole thing, what do we use for the mass? The whole thing. We use, what is that going to be, 34 kilograms? Now, here we're only going to use 8 times 9.81 because that one is the only one that's being pulled on by gravity. We'll make it negative, though, because it's to the left. This is going to be 6 times 9.81, and it's positive because we've got it drawn to the right. The right side is going to be negative 19.62, and A is going to be, I'm going to say 0.6. Anybody have that? Negative 0.6? Negative 0.58 meters per second squared. 2 digits, right? 2 digits, 2 digits. Final answer should be 2 digits. Guys, if you had made this one positive and this one negative, what would you have got? Positive 0.58, right? Does it matter? No. Good. Harder than the first question we did like this? Not really. Not really. Just get this thing in the middle. You can imagine how maybe we can make this a little bit harder. Throw friction into the mix here. Okay, let's say we had a force of friction acting. It would act to the right because the system moves to the left. And we just add it in right here. Okay, again, doesn't make it any harder, just a little bit more work, that's all. All right, if that's okay, then let's take a look at these two practice questions, please. Page 157. All right, everyone, let's take a look at number 2 then, okay? It says, if a tire in example 3.11 is replaced by a tire of mass 15 kilograms, what's the acceleration of each object? So let's go here. My tire is 15 kilograms. My pail B, I think, was 8 kilograms, wasn't it? Is that right? Is that what it was? 8 kilograms? And pail C was 6 kilograms. What's the acceleration going to be now? Well, let's straighten it out. If we do that, then pail B has a force of gravity acting on it. We'll call it FGB. Pail C has a force of gravity acting on it. We'll call it FGC. This is 8, this is 15, this is 6. The net force is equal to the sum of the forces FGB plus FGC. That's it. The mass that we're going to use here is 29 kilograms. It's the total mass times the acceleration equals 8 times negative 9.81 plus 6 times positive 9.81. Okay, we're going to get 29 on the left-hand side here still. It's equal to negative 19.62 on the right-hand side. Do the math there. A is equal to negative 0.68 meters per second squared. Now, the question asks me for the acceleration of each object. What have I found here? If we go back to the semi-truck ice cream analogy, I found the acceleration of the semi-truck, right? Can you tell me what the acceleration of each box of ice cream inside the semi-truck is? Same as the semi-truck, right? So if I get negative 0.68 for the whole system, then object B, pail B, is accelerating downward at 0.68. Tire A is accelerating to the left at 0.68, and pail C is accelerating upward at 0.68 meters per second squared. Okay? All right, here's another one. This one's going to be a little bit trickier, though. Those of you who like tricky questions, it's a little bit trickier, but not too bad. I'm going to give you one either tomorrow or Monday that's going to be a combination of everything, all of this stuff that we've done. It's going to be the greatest question ever. You're going to love it. Some of you are. Some of you are going to hate it. Okay, this is the last thing that we have to do before we see that question. It says a 3.5 kilogram block is sliding down an incline of 15 degrees. The surface of the incline supports, or exerts, I should say, a force of kinetic friction, so it's moving. We don't have to worry about whether it's static or kinetic. We know that it's moving. It's kinetic friction, 3.9 on the block. What's the acceleration of the block? Well, in theory, this question is no more difficult than anything else we've done. We draw a free body diagram. F net is equal to the sum of the forces. Solve for the acceleration. The problem is this. Look, it's sliding down the incline. There's a force of friction opposite to the direction of motion. That's easy enough, right? It's 3.9 newtons. What pulls it down the hill? What pulls it down the incline? Well, gravity would pull it straight down. Right? Gravity acts down. And if it's just gravity that's pulling it down the hill, then it's not going to slide down the hill. It's going to go straight through the ground and down. So there's got to be something else as well. Yeah. The normal force. Which way does the normal force act? Straight up? It acts 90 degrees to the surface. So we're going to have a force of gravity acting straight down, and we're going to have a normal force acting up like this. Now, when we combine the normal force with gravity, we add those two together vectorially, we're going to get a vector right here that is parallel to the hill. I'm going to call it FH, the force of the hill. I'm going to redraw it up here. It's not like it's another force. There's not two FHs. There's only one. I'm just drawing it in two different places. Think about that. If this thing moves down the hill, there has to be a force that acts down the hill. The force that acts down the hill isn't really a fundamental force. It's a combination of these two forces, the normal force and the force of gravity. So if we can get that value of FH, okay, the combination of the normal force and gravity, then we can pay attention to FH and FF and solve this problem as easy as any other. But the problem is getting the value of FH. Pay really, really close attention to the next two things I'm about to say. One, this angle has to be 90 degrees. Has to be. Fn plus Fg, when we combine those two forces, they must give me a force parallel to the hill. And if those two forces are parallel to the hill, or sorry, if FH is parallel to the hill, then that angle between Fn that's perpendicular to the hill must be 90 degrees to FH. Has to be, every time. So don't ever draw it like this. Some people will try this, right? Don't do that. That's wrong, and it's wrong every time. This angle right here between Fn and FH must be the one that's perpendicular. Has to be. Now, the second thing that I want you to recognize is that this angle right here, at the top of that, will always be the same as the angle of the hill itself, 15 degrees. Now, we can justify that. Okay, that's 15. This is 90 right here. This is 15 and 90 is 105. This would be 75. Since this is 90, this would be 15. You go through that process every time, and you're going to find that the angle there is always the same as the angle of the hill itself, right here. So you don't even need to go through that process. It's always the same. We know that that angle down here is always 90 degrees. We know that this angle up here is always the same as this angle right there. Now let's get FH. Let's say sine 15 degrees is equal to opposite over hypotenuse. Opposite is FH. Hypotenuse is force of gravity, m times g, 3.5 times 9.81. Take both of those numbers up by multiplying. 3.5 times 9.81 times sine 15 gives me 8.88655 newtons. Does that make sense where I got that value from? I got a right angled triangle. I want to find the adjacent side, and I have the hypotenuse, or at least I almost have the hypotenuse, the force of gravity. It's m times g. So now we know FH. It's 8.88655 newtons. There's not two of them. I found this one, but this one up here is the exact same thing. I've just drawn it in two places. Now this question's easy. Now I've got a 3.5 kilogram object. If I straighten this out, with a force of friction acting this way, of 3.9 newtons, and a force of the hill acting this way of 8.88655 newtons. We'll do our thing. The net force is equal to the sum of the forces, FH plus FF. Hey, why do I not have to include Fn and Fg there? Why is it not FH plus FF plus Fg plus Fn, the normal force? They do act. Right? Normal force and gravity are both acting there. Why am I not including them down here? Yeah, I already have. I am including them. Look, FH. What is FH? It's gravity and the normal force. So I'm already including them. I'm just doing it in a simpler looking way. I've found the value of FH. I've combined them, and then I'm including them instead of including them separate, right? So the net force is m times a. It's 33.5 times a equals negative 8.88655 plus positive 3.9 newtons. Let's get the value of A there. I get negative 1.4. Anybody else get that? Is this a harder question? Yeah, I think it is. I do. What makes this one harder? Well, it's certainly not this stuff over here. Yeah, that's exactly the same as we've been doing for the last couple of days. Makes it harder? This little stuff up here. Okay, but if you remember to always draw that free body diagram, gravity acting down, normal force acting perpendicular to the surface, and then that force of the hill acting perpendicular to the normal force, it's not so bad. It really isn't. Get FH. Sometimes FH, some places you see it called F parallel. Why do you think we call it F parallel? It's the force that's parallel to the hill, right? I call it FH. Doesn't matter what you call it. Okay, we need that value. Once we have it, easy question, just like it was before. Okay. Homework. Page 179, questions 1 and 2. See what you can do with those tonight, please. Keep the example that we just did as a guide. Keep it right beside you. Follow along with it. Don't try to skip steps. Okay? You're going to be able to do this if you don't try to skip steps and if you use that as a guide. Okay, let's see what you can do.